Before we dive into the preparation process, there are two things I'd like to mention. First, you don't need any prior experience with standard Three.js. However, a basic understanding of fundamental React concepts is essential. Specifically, you should be familiar with creating components, using state, and working with hooks. Secondly, I have a written version of the entire tutorial. This will be helpful if any of the content in my videos becomes outdated, as you'll find the updated version in the article. And with that in mind, let's get started. First, create a folder and then open it in VS Code. Next, open a new terminal and run the following command: npm create vite@latest, followed by the name of the project folder. This will set us up with the latest version of the bundler. Choose React, then JavaScript. With that done, open the new folder, then open a new terminal and run this command: npm install to install Vite and the other dev dependencies. Next, run the following command. This will install the core Three.js library in React 3 Fiber. The next step is to run the dev server with the command npm run dev, then left-click plus Ctrl to open the project's main page. Finally, in the main JSX file, ensure that the app component returns only a container div. We can discuss a React 3 Fiber app without mentioning the following three essential components. The coordinate system. Actually, we can discuss 3D at all without a 3-axis coordinate system, as it serves as a tool for measuring and defining positions, orientations, and transformations within the 3D space we are working in. The coordinate system in React 3 Fiber is right-handed, which means the forward direction is represented by negative values, while the backward direction is represented by positive values. Additionally, the z-axis represents the forward-backward directions, while the y-axis represents the top-bottom directions. Secondly, we have the scene. The scene is the 3D space in which we add our objects, including meshes, models, lights, etc. And thirdly, the camera. Just as shows in movies rely on a camera to capture the action within a certain space in a scene, the same principle applies here. In other words, the camera determines the perspective and visibility of the scene's content. And with this in mind, let's create our first React 3 Fiber app. First, import the canvas component and add it to your app. This creates a canvas element that encapsulates the three elements we've just discussed. The canvas is currently invisible because it has a white background, so let's change that. Now you'll likely want the scene to take up the full size of the page. To achieve this, we need to make the parent element of the canvas match the size of the window, as the canvas will inherit its size from the parent. As you can see, this works fine, but personally I prefer to separate the CSS into a different file. To do that, I'll delete this and add it to the index.css file after removing the default code. So we ended up with a full screen scene, but with some extra scrolling space. To remove it, we just need to eliminate any default margins applied to the body of the page. In React 3 Fiber, objects are referred to as meshes, and a mesh is composed of two components. The first component is the geometry, which defines the shape of the mesh. The second component is the material, which defines the surface of the mesh and how it appears, particularly when affected by different types of light. So to add a sphere to the scene, I'll create a mesh component with two children, the sphere geometry and the mesh basic material. Of course, there are various properties we can modify, with the most obvious one being the radius of the sphere. To adjust it, we use the args prop, which accepts an array of arguments. Specifically, the first element in this array is the radius. As you can see, the sphere is larger, but it doesn't appear smoothly rounded. Actually, let's add a couple more arguments to the array and observe how its shape is affected. Now, you might be wondering why the sphere isn't rounded and what are the new arguments that I've just added. Well, in React 3 Fiber and in the field of 3D graphics in general, the geometries of meshes consist of a set of triangles formed from points, also known as vertices, and segments. With that being said, the more segments and vertices a geometry has, the smoother and more detailed the mesh surface becomes. Returning to the sphere, the default number of geometry segments was insufficient to make the mesh perfectly rounded. Additionally, reducing the number of segments further made the sphere look even less rounded. We can visualize these segments by activating the wireframe mode in the material. Now let's increase the number of segments and observe how the sphere changes. By the way, the second element of the array represents the number of width segments, while the third element represents the number of height segments. React 3 Fiber offers various geometries that we can use, so for example, to add a cube we can use the box geometry. To change the dimensions we use the arcs prop. The first three elements of the array are the width, height, and depth. Now to change the material's color we need to use the color prop. We can use the name of the color or its hexadecimal representation. Just like with geometries, there are many materials to choose from depending on the case. That said, let's use the mesh fong material this time. As you can see, the color information is lost because materials like mesh fong material require light to be visible. So let's add a light source, and by the way, I'll cover more about lights in a future video. As you can see, the color now appears but looks dark because we are viewing the cube's shadowed side, which is minimally affected by light. So what we'll do now is move the camera to view the highlighted parts. To do that, we'll use the camera prop in the canvas and set its new position. We also have the mesh toon material, which gives objects a cartoonish look. For a better visualization of the effect, I'll use the torus knot geometry this time. We can apply three different geometric transformations to this mesh, with the first being translation. To do this, we can use the position property, which takes an array of three values, each representing a translation axis, and as you can see, we've already used this one to position the light. Next, we have rotation. And finally, we have scale. Bear in mind that these transformations can be applied in various ways, and most importantly, their values can be set dynamically rather than being hard-coded. Videos, animations, and games are essentially sequences of images or frames displayed at a specific frequency, and React 3 Fiber scenes are no exception to this. Say we want to animate a jumping ball, like in this example, we need to capture a sequence of frames while the ball is at a certain position in each frame. That being said, in React 3 Fiber, this happens behind the scenes through a mechanism called the render loop. Simply put, the render loop continuously captures the scene and displays it as updates occur to any of its components. So let's create and animate a simple box to see how this works. First, let's move the light outside of the mesh, which was a mistake I made in a previous video. However, this approach can still be valid in certain cases if done intentionally. Next, we'll create a component that generates a box mesh, so there is nothing special about this step. And now it's time to animate this cube. To do this, we first need to import the useFrame and useRef hooks. We'll use the useRef hook to create a reference to the mesh, allowing us to access its properties. And we'll use the useFrame hook to update the mesh over time. That being said, any logic placed in the body of this callback function will run repeatedly every frame, which could be 60 frames per second or more, depending on the display device. Here we'll animate the box by rotating it, dynamically increasing its rotation value by 0.005 units for each frame. Up until now we haven't had control over the camera's perspective. The camera has remained in the same position, looking in the same direction, so this is when camera controls come in handy. For that we'll need to install a new module, which is an extremely rich package of powerful features. This module is called Drei or Drei in German. Now that we've installed Drei, we have various camera controls to choose from. The most common ones are first-person controls and orbit controls. First-person controls give you the freedom to move the camera just like in first-person shooter games. That is, by using the mouse buttons and arrow keys on the keyboard. To use it, we simply need to import it and integrate it within the canvas component. In addition to that, we have several properties that we can enable or update, like the camera movement speed. Another example of a property that we can enable is auto forward, which is self-explanatory. Next, we have orbit controls, which allow the camera to orbit around a specific point. Again, to use it, we just import it and integrate it into the canvas. And similar to other camera controls, we have a variety of properties that we can modify, such as the target point to orbit around, enable pan, enable zoom, and more. Helpers and gizmos are utility objects that assist in visualizing or debugging aspects of a React 3 fiber scene. There are many of them, but in this video we'll try just a few. So I'll start with the axis helper, which displays the X, Y, and Z axis of the scene's coordinate system. The helper isn't displayed because it's hidden by the box, as its axes aren't long enough to extend beyond it. So what I'll do here is simply add the args prop and pass an array, with the first element being the new length of the axis. I mentioned adding the helper to the scene, and I did, but we can also attach it to objects. The second helper we are about to see is the grid helper, which displays a grid. Here 20 is the size of the grid, and we can add another argument, which is the number of subdivisions. The third array element is the color of the two main axes of the grid. The fourth element is the color of the remaining lines. Now, to add gizmos, we need to import the following components from Drei: Gizmo Helper, Gizmo View Cube, and Gizmo Viewport. First, I'll add the Gizmo Helper. This component serves as a wrapper for the actual gizmo. We need it to place the gizmo using the alignment prop, and we can also add some margin with the margin prop. And here we'll specify which type of gizmo we want to add. Manually changing values to test various settings can be somewhat frustrating and time-consuming. That said, a fantastic debugging tool we can use is Leva, which offers a user-friendly interface that allows us to update values in real time. First and foremost, I'll install the module by running the command npm install leva at 0.9.34. I chose this specific version because the latest release has a bug related to the color picker.
2,000 years later.
Now that the installation is done, I'll import the useControls hook. Next, say we want to control the rotation speed of the box using a slider. To do that, I'll create a variable that will be assigned the value from the slider. Here, we'll set the initial value as well as the minimum and maximum values that we can get from the slider, along with the step increment. Then we'll use the speed variable instead of the hard-coded value. To add a color picker to change the box color, I'll create another variable, and once again I'll set an initial value and then use the color variable instead of the fixed value in the color prop. Light is one of the most important components in React 3 fiber scenes. That being said, in this video we'll explore some of the most commonly used types. Ambient light is the general diffused light present in a scene that doesn't come from a specific direct source. It represents the soft illumination that evenly lights all objects. To add ambient light to the scene, we simply need to create an ambient light component. We can control the light intensity and color using the intensity and color props. Next, we have directional light. This type of light doesn't have a specific source. Instead, it emits parallel rays that cover the entire area, and the best example of this is sunlight. To add directional light, we need to create a directional light component and specify its position, which rather defines the direction of the light. Of course, we also have the intensity and color props to control the light's brightness and color. The third type is spotlight. Unlike directional light, it has a specific source and illuminates a limited cone-shaped area. This type of light is commonly used in theaters, and it's also associated with aliens pulling humans up into their UFOs. To create a spotlight, we need to create a spotlight component, and unlike ambient and directional light, the intensity should be set in the dozens. As you can see, the light is present. However, testing different values to achieve the perfect position and other properties, particularly the angle, can be time-consuming and require significant effort. With that being said, using a helper, specifically a spotlight helper, can be extremely beneficial, especially when paired with Leva. So, first things first, we'll create a custom spotlight component. Next, we'll import the useHelper hook from Drei in the Spotlight Helper class from the core of Three.js. In the custom component, we'll create a reference to the light and then attach the helper to the spotlight using the useHelper hook, which takes 3 arguments: the light reference, the Spotlight Helper class, and a color for the helper segments. And there we go. Now we can take it a step further by controlling the light properties using Leva and observing how the light helper adapts in real time. To achieve this, we'll update the radius of the light's angle. Another property we can adjust is the penumbra, which adds a gradual blur to the edges of the spotlight, creating a softer transition between the light and shadow. Lastly, we have point light, which has a specific source and emits light in all directions. A candle flame is the best example of this type of light. To create a point light, we'll need to create a point light component and set the intensity and position props for the light source. To make objects cast shadows, we first need to activate this option by adding the shadows prop to the canvas. Next, we need to specify which objects are shadow casters and which are shadow receivers. To do this, we'll use the cast shadow prop on shadow casting objects like the box and the light in our case. Then we'll use the receive shadow prop to enable an object to receive shadows. For this, I'll create a plane and rotate it. As you can see, the shadows are displayed correctly and everything looks fine. However, there may be cases where shadows appear clipped or fail to appear entirely. Actually, let me provide an example of that. So I'll start by creating another light source with a helper, but this time I'll use a directional light instance. Next, I'll import the appropriate helper and use it instead of the spotlight helper. By the way, ensure to set the arguments in the correct order. When using the useHelper function with a directional light helper, there is a size argument that comes before the color. This small detail cost me hours to figure out, so avoid making the same mistake. And there we go, we've got our light with its helper, and as you can see, most of the box shadow has mysteriously disappeared. So why did this happen? When the light is set to cast shadows, it uses a rectangle that defines the area where the shadows appear. Any shadow cast outside the bounds of that rectangle will not be visible. That being said, let's use a helper that allows us to visualize those shadow limits. First, we need to import the camera helper from the core of Three.js, create a new reference for the shadow, and then call useHelper passing the reference and the helper as arguments. Next, we'll set the directional light as a parent component. Inside it, we'll create an orthographic camera and attach it to the shadow. Now you might be wondering what's the deal with this camera and how does it relate to shadows? Well, let's take a moment to understand what we've done so far. If you remember from the second video in this playlist, I mentioned that the camera is one of the most essential components of our React 3 Fiber app. However, I didn't create any camera until this video. The reason behind that is that a perspective camera is implicitly created and attached to the scene by default. That said, we can still add a camera if you want to, and it will automatically be attached to the scene, but that's not exactly what we want in this case. What we need is an orthographic camera which is defined by 4 edges and attached to the shadow, not to the scene. We achieved this by using the orthographic camera component and the attached prop. The 4 edges defined by this camera now correspond to the same edges of the shadow's area, so when we use the dedicated helper to display the camera's edges, we are essentially showing the bounds of the shadow area. Now, taking a look at the result, you can see a new helper displaying a shadow area defined by the default values that come with the orthographic camera. This means that by updating the values of the camera edges, we can adjust the bounds of the shadow area. To do that, we'll use the args prop and pass an array of 4 values representing the left, right, top, and bottom edges of the shadow area, respectively. And there we go. After adjusting the values, the box shadow has appeared, but it's still not fully complete. So to fix this, we need to widen the area on the right side. We can do this by updating the second element of the array. Alternatively, we can skip the args prop entirely and use the specific sides by their names. So here I'll use the top prop to adjust the top side and the right prop for the right side. To add models to your scene, first place the files in the public folder of your project. Now, when it comes to the code, we've got 2 options. The first is using a combination of the useLoader hook and a loader, so let's start by importing them both. And here, since we are working with gltf files, I'll import the gltf loader from the core of Three.js. Next, we need to create a new component where we'll call the useLoader hook. It takes 2 arguments, the loader type and the path to the model file. Then we'll return a primitive component with the model passed to its object property. Before we proceed, let's understand what a primitive is. So, as we've seen throughout this series, every part of a React 3 fiber scene is represented by a component, whether it's a light source, mesh, material, geometry, helper, etc. That said, some objects don't have a corresponding component, and loaded models are one example of this. So, what do we do in this case? Exactly, you got it right, we simply use the primitive component. Back to the code, now we'll add the model component to the canvas, and that's it. By the way, your model will most likely appear completely black if you don't have a light source in your scene, so make sure to add one. And there we go. Now we can treat the model the same way we do with other objects. For example, if we want to move it, we can use the position prop on the primitive component. And that's the first way to load the model. The second is almost the same, except that we'll use a hook from Drei that corresponds to the type of file. So once again, since I have gltf files, I'll import the useGLTF hook. Then I'll create another custom component, called the hook, and that's it. To apply textures to an object, we need to make a custom component, so let's jump right in. Now that we've created the mesh, it's time to load the texture we want to apply. Actually, there are two ways to do this. The first is by using the useLoader hook, which we used in the previous tutorial for loading models. This time though, we'll use it with the texture loader instead of the gltf loader, since we'll load the texture obviously. By the way, make sure you have the images in the public folder in your project directory. Now we'll pass the texture to the map prop in the material component. The second way to load the texture is by using the useTexture hook from Drei. Applying a texture to a box is no different from applying it to a sphere. So we'll create a custom component, use one of the two methods to load the texture, and then pass it to the material. This will give us a box with all 6 faces displaying the same texture. But what if I want a unique texture for each face, you might be asking. Well, to do that we'll need to pass a unique material with a unique texture to each face. Usually when we pass a material to the mesh, it gets applied to all 6 faces. However, if we want 6 unique materials for the faces, we'll pass 6 materials, each for a specific face, using the attach prop. The scene itself isn't an exception to the rule, so we can map a texture onto it. That said, we'll just need a way to access it, since it's created implicitly. To do that, we'll use the useThree hook, so I'll also import the color class to change the background color before moving on to applying textures. Now, to change the background using a texture, we'll load the image and assign it to the background property instead of using a color instance. As you can see, the image is displayed, but it looks washed out, and that's because the texture isn't set to the correct color space. In case you're not familiar with the term color space, this video is definitely a must-watch. So to fix that, we'll simply import the sRGB color space object from the core of Three.js and assign it to the color space property of the texture. Finally, a React 3 fiber scene is essentially a box, which means we can map unique textures to its faces, just like we did with the box. This is helpful for making your scenes feel like real environments. That said, to change the background this way, we have two methods. The first one is once again using the useLoader hook combined with the cube texture loader this time. The second and easier way is by using the useCube texture hook from Drei. Picking objects in a React 3 fiber scene is pretty straightforward, especially compared to doing it using standard Three.js. For example, let's say we want to enable wireframe mode on this box when it's clicked. To do that, we'll use React state to keep track of the current state of the box wireframe property. Next, we'll create a click handler function to toggle the wireframe value using a conditional ternary operator. Once that's done, we'll pass the value to the wireframe prop in the material and attach the click handler at the mesh level. And that's pretty much it. To add background sound to a React 3 fiber scene, we need to use standard Three.js classes since there isn't a built-in component for that. That said, we'll need the following classes: Audio Listener, Audio, and Audio Loader. As defined by the Unity docs, an audio listener receives input from any given audio source in the scene and plays sounds through the computer speakers, and for most applications it is attached to the main camera. An audio object holds the data from an audio file, which is loaded using an audio loader. So we'll start by importing the useEffect hook along with the classes I mentioned, and then I'll create a new component. Now, as stated in the definition, a listener is usually attached to the camera, so we'll use the use3 hook to access the camera. Next, inside useEffect, we'll create a listener and attach it to the camera. With that done, I'll create an audio and audio loader instances to load data from an MP3 file that I have already placed in the public folder. The buffer variable is used to fetch data into the audio instance through the setBuffer method. Next, we can set a variety of sound properties such as volume, autoplay, loop, etc. Finally, we'll set it up so that the sound plays when the user clicks on the window, as modern browsers require a user gesture to play audio on a web page. In reality, the volume of the sound depends on the distance, and we can replicate this in a React 3-fiber scene. This means we can place a sound source within our scene, and the volume will adjust based on the distance between that source and the camera. We can achieve this in two ways. The first method is by using the positional audio class instead of audio. So, I'll import the class and create a new component which returns a mesh representing the sound source. Next, we'll create a reference and attach it to the mesh. Then, as I mentioned, we'll use a positional audio object instead of audio. setRefDistance sets the distance at which the sound plays at its original volume. Then, of course, we'll assign the sound to the reference. The second method to add positional sound is by using the positional audio component from Drei. So we'll start by importing the component under a new name, since positional audio already exists. Next, we'll create another component that returns a mesh. Here we'll only need a reference and we'll play the audio only after the file is loaded. Now in the mesh we'll add the new component and assign the reference to it instead of the mesh. We'll also pass the properties as props. Finally, this time we'll play the sound when the box is clicked instead of the window, because why not? And that's it.